So now let's see at this new kind of question. It's slightly different from what we have done earlier. No pulleys over here, no strings over here, so no strings attached. Now if I move the block that way, or it goes that way, if the block goes that way, then this green block is going to come down. And conversely, if I push this block this way, then the green block is going to go up. Now what happens naturally is not the question over here. The constraints are the question. If this remains in contact with the other thing while it is being pushed, or while this goes down and that goes away, these two are going to remain in contact, then what is the relation of the bodies? So let me call this body as this is body B over here in green, and the purple one is your body A. So what we have over here is, say the velocity or the displacement of this body is, say we'll work with velocity. Velocity is VA, and this velocity will be downwards with VB, and surely they are constrained. Their movement is not independent. If this moves by say X and this moves by Y, then the movement is constrained. Now how much will it be? You can make a diagram, you can make this go in and see how much it goes up, and note any one point on the body and see what happens to that point, where it is and where the other guy is. So in fact I'll make that first so that you have a good idea of what is happening. So say the block has shifted forward and is here now. So this point would have shifted an equal amount, so I'll draw this here, and that's the new position of the wedge. The dotted position is the new position of the wedge. It has gone forward by X. Any one point over here, maybe this point, that has also gone forward by X, and it is here now. At the same height, the points are same. So this point is here now. So you call this point as point P, then that's your new position of P. Similarly, this block I'll redraw. It would have come down. It would have come down vertically, and it would be over here. So say it has come down by Y. So this amount, this amount, what it has come down is Y. So what we see over here is we have a triangle formed. I'll draw in a different pen. So we have a triangle formed over there. You can watch over there. That's your Y. That's your X. So, and obviously this was along the incline. So this was along the incline. So this angle was your theta. That was the angle of the incline. So what is theta over here? In this diagram, this is your theta. So we have a relation between X and Y. What is the relation between X and Y? Clearly tan theta is equal to Y by X over here. So what we say is Y will be equal to X tan theta. So if this moves by X, this is going to come down with Y equal to X tan theta. So that is solved. Now there are a number of ways of doing it, as I've listed so many methods. So one is drawing. I'm drawing so that you understand how it is happening, what is happening. You need not draw all the time. So this is what has happened. Now what you can do is, to solve such questions, you can again use work done by internal force is 0. Now what is the internal force over here? If these two bodies are taken, then the normal reaction on this and the normal reaction on that, N and N. So how much ever this point, or how much ever the work is done by this force, so is equal to the work done by that normal reaction in the other way. So net work done would be 0. So how do we solve it? I'll just draw this part over here. That's your normal reaction, that's your point, and that's your plane. We say the body has gone forward by X amount. So if it has gone forward by X amount, how much it has gone in the direction of N? So we have to do a N dot X to get the work done by N. So how much it has gone in the direction of N? So in the direction of N, this angle was your theta. So this angle over here is your 90 minus theta. So this angle again becomes theta. So this angle is again 90 minus theta. So n cos 90 minus theta is the n in direction of x, or x cos 90 minus theta is in the direction of n. So it is x sine theta, which is in the direction of n. So what we get is that the work done by this normal reaction is n x sine theta. Now for this body, that's the body, that's the point, that's the normal reaction, and we are saying that the body is going down by say y amount. Now again, let us get the angles clear and how much is the y in the direction of n. So basically let me get this angle for you. How much is that angle? So before writing the angle, let us have it over here. This angle is theta. This angle is 90 minus theta. This angle is 90 degree. You have theta. So this is a right angle triangle. That's your 90 minus theta. This is your 90 degree. So this angle must be equal to theta. So anyways, that's a general knowledge. If you have theta with the horizontal, then the normal makes theta with the vertical. Remember that. If the horizontal makes theta with the incline, then the normal to the incline makes theta with the normal to the horizontal, which is the vertical. So if a wedge is inclined at theta to ground, then the normal to the wedge will be inclined to theta to the vertical. Okay, so what do we have? How much is the movement? So the y along n is y cos 180 minus theta, but you have done in trigonometry, that is minus cos theta. So we can say that it is minus y up and cos theta along n. So it is minus y cos theta along n. So the work done is minus n y cos theta. The total work done will be 0. By those two forces, the work done will be equal and negate each other. Total will be 0. So what we have is n gets cancelled because it is action reaction force. This normal reaction on the two bodies are equal and opposite by the third law. So same as we were doing in method 3 over there. So what we get? We get is x sine theta is equal to y cos theta. So your x or y, what were we finding earlier? Y. So what we get is y is equal to x sine theta by cos theta, which is your tan theta. Same as the answer earlier. You might think that the drawing was easier, so then you can go with the drawing. At times you feel this, if you are too much into work done and all, which is the chapter after your laws of motion, so you might be inclined to do through work. So work done by the n on this body and that body, you can take it as equal and opposite because n and n are internal forces. So work done totally by them has to be 0. So we can use that. So more details on the normal reaction and everything I will be doing when we do, and we can have a better explanation of this when we do laws of motion. So here, just for the constraint sake, any other way would you like to do? That is it's a sort of, again, if I do a variation of method 2 over there, it will be a sort of the diagram again what we are drawing. So diagram is pretty safe to go with. Now you're cross checking. If you want to cross check whether you have got it right or wrong, then yeah, that's a good idea. And you can cross check with various angles. See, if the angle was very shallow, then what happens? If you move the wedge, maybe whichever side, if you move the wedge that side, it is hardly going to go down. So your y is almost equal to 0 if theta is almost equal to 0 is what we are seeing. So is that right? Yes, when we put tan theta, theta is 0, y is almost equal to 0. So at least that is coming all right. And suppose you had a very high angle, very high angle, that's your wedge, very high angle, that's your theta, and that's the object on the wedge. So what happens over here? If I move by x, if I move by a little x, what is going to happen? It is also almost going to fall down a lot of lot of distance. So if it is totally vertical, just 1 degree, if I move a very little amount, it is going to go down a large amount. So that means if x is very small, still y will be very high if angle is very high, if angle is almost 90 degrees. So is that true over there? X is very small, but tan theta is almost 90. So tan at 90 is almost infinity, because it becomes sine by sine 90 by cos 90. Cos is almost 0, so it becomes almost infinity. So this y becomes almost infinity, which is the case what we are seeing over here. It becomes a very large value even if x is 0.00001 millimeters, and this is tending to 90 degree. It is just short of 90 degree, 90 minus, then still your y will be a very large y, because tan theta will be almost infinity. So it is almost verifying, and at 45 degrees we can imagine, like if the wedge is 45 degrees, then the movement by this and the movement by this is, by intuition, it has to be same. So that is how you verify your formula. It is best to verify once. Suppose by mistake you got cot theta, then you will get cot when you are verifying using this method. So very similar setup would be, it is the same setup in fact, drawn in a different way. They make wall on two sides instead of this wall. They have made this wall, and you'll have an object which can slide down, object which can slide down on another object where the inclines are matching, same as this part where the inclines are matching. So it's the same thing, it comes down and it goes away. So answer will also be the same. In the same case, you can draw and check. You can do normal reaction here and here, say that this movement of this thing is y, find out the force. Say the movement of this thing is x, find out the work, not the force, sorry, find out the work by this normal reaction. With this y, find out the work by this normal reaction, n and y in that component. So n dot y you do, and n dot x you do, and should be equal to 0. So you'll get what we got over there, that equation. So let me give you something which is having pulleys also and angles also, and let's see what you do about it. So that's our next question. Here we have a pulley also, and there's a wedge on which there's a body. So both kinds of constraints are over here, and we have to find if the body B moves by a certain amount, say x, then where will body A move and how much? Now if B is moving this way, it is going to swing down a bit and it is going to go somewhere over here. So we have to find exactly how it is going and how much, with what velocity. If the velocity was v, then what is the velocity of that? So it has moved dx, then what will be the displacement of the body A? That is what we are going to do. It is clearly a constraint. This body cannot pierce into the wedge. That is one constraint. The rope is going to be tight always. That is another constraint. So with whatever force we are moving this body, with whatever force, with itself normal reactions and all is moving, or we are assisting it by putting some force, if a certain distance x is moved, it is going to move a particular distance y. It is not going to be a force dependent thing. So it's a constrained, it is a constrained motion between A and B. It is independent of how much force we put. The displacement of this and displacement of A is constrained. So first we have to figure that in our minds, so it's a constraint or not. Yes, it is a constraint, and every time we move an inch this side B, A is going to go to a particular position only all the time. So like this and the one before, we can discuss everything in terms of work, but I would rather ask you to make the diagrams and get the actual positions, how it is going, so that you have a better idea of what is happening, and then we will deal this in two different ways. So since I'm going to deal it in two different ways, let me make another diagram over here for this. That's your angle theta. There's a pulley on it, and then there's a body A attached to the string. That's your ground. Okay. So if this big mass, if this body B goes here by x, it is somewhere over here, then again I am going to draw the same diagram. This would have moved by x, this point has moved by x, and this is the new position. That's the new position, and that's your pulley. So pulley would have come over here somewhere. So that's the new position. So this part of the string remains as it was. Rest will bend, and it is going to go in here like this, and the body will be somewhere over here. Now we have to get how much is the movement and what is the direction of the movement. So we'll use vectors to do it. What we'll try is using the vectors. So say the velocity of B this way is VB, that is with respect to ground. So that is velocity B with respect to ground is this way. Now velocity of A, that's your A, body A, velocity of A with respect to the body B. What do you think will be the direction with respect to body B? With respect to body B. So that's the key over here. With respect to body B. Meaning to say that body B is not moving. How does body B perceive everything happening? So actually the body B had gone to the wall. But for body B, what is happening? If you are on body B, what do you feel? You feel the wall is coming towards you. The wall has come towards you so much. So for body B, the wall has come in. The wall, you have moved X. Body B feels as if the wall has come in by X. So if the wall comes in by X, if it comes in by X, what happens? It's this one A is going to slide down on body B by X. So A is going to slide down on body B by X, if that's the velocity of body A with respect to B. So if B was going with VB with respect to ground that way, that was your X, what I'm saying, then the body feels that the wall is coming towards the wedge with a velocity of the same thing, B with respect to ground, and that is how much this body is going to go down along the slide. So if I have a mark on the slide, say I'll put an orange mark. So if this other edge this is a mark on the body. So later on, the body A will be somewhere X. If it has gone X forward, it will be X down. It will be X down, and the position of the body will be something like this. So try to understand this. With respect to the body, it would have come over here. So the body would have come over here, and this distance would also be X. But the wedge itself has gone forward. Whatever this point was P earlier and this point was Q, those are the points on the wedges. On the wedge, that was your P and that is your Q somewhere. So there is where your P is. I've drawn the thread a little less. It is that much more. So P has come over here. That's your P. And Q has come over here. That's your Q. And the body is here. Finally, the body is here. Okay, so this diagram is clear. I'll make it over there further. So what we see is this string has increased by X length. This part of the string has decreased by X length. This part of the string has increased by X length. It has gone down, and this has gone down along the wedge with a distance of X. So it is pretty easy now. What we have to find is velocity of A with respect to ground. What we know is velocity of A with respect to B and velocity of B with respect to ground. So I hope you remember how to connect these vectors. Velocity of A with respect to ground would be equal to velocity of A with respect to B plus velocity of B with respect to ground. So I'm doing it deliberately in the vector way because we have done this a lot earlier. So I just want to make use of that equation. You have done a lot of study with this equation, so we'll use it. So we know velocity of A with respect to B, velocity of B with respect to ground. So what is velocity of A with respect to ground? So we'll draw the vectors. What is the velocity of A with respect to B? Is a vector which is along the slide. So I hope I make it almost parallel. So that's your velocity of A with respect to B. This angle is exactly along the slide because A with respect to B is along the slide. With respect to B, A was just going down the slide as if B is not moving. So this vector has an angle of exactly theta with the horizontal. Okay. plus velocity of B with respect to ground. So velocity of B with respect to ground is horizontal. Now what's the magnitude? Fortunately, the magnitude of both of them are same. We have discussed that. So A with respect to B would have gone down by x, and B with respect to ground has gone by x. So the magnitude of velocity of B with respect to ground, magnitude is equal to velocity of A with respect to the body B. So these two magnitudes are same, both were x and x in a given time. So this will fall short of the vertical, this will exceed. So here it's an isosceles triangle, so the resultant direction is this. It is bound to be backwards. No matter what, it is going to swing back, it is going to come back. So maybe this is not a very clear depiction. It comes back a bit, it comes back. Why it comes back? Because this line is going to exceed this line. This was at an angle and this is horizontal. So what we see is this body is bound to be back. By this constraint, it is bound to go back. Why? Because this x is equal to that x. That is what we have seen. If it goes by x, then this goes down by x. But if the body has moved by x, if the body has moved by this x, this point, this A has gone down by x, but the body has moved back by x, this x is going to exceed that line vertically and it is bound to come back. Now with forces, we may analyze it later on. You have for this body, for the body A, you have a normal reaction acting on it, you have tension acting on it, and you have mg which is down. And if I have to just consider the back and forward thing, you'll have a tension component in the front, and you'll have a tension component, and you'll have a normal reaction component at the back. What we can safely say is tension component in the front will always be greater than normal reaction at the back. When we do forces, we'll analyze that. For now, just come back to this situation. So what we have done is we have used our vectors concept. We have figured out the velocity of one with respect, we have given velocity of the wedge with respect to the ground, figured out the velocity of A with respect to the wedge because that was easier to figure out in this case, and we have got the actual velocity of A with respect to ground. So now how to calculate this? The calculation is pretty simple. This angle is theta because this VAB was along the incline, so fortunately it's the same angle, theta. So just on this triangle we can use vector formula, or we can just get the horizontals and verticals. So this vertical is x sine theta. This horizontal part, this small horizontal part, is x minus x cos theta, because this much is x cos theta, this totally was x. So you have x minus x cos theta. Hence that orange line, the displacement of that is going to be, the displacement of A with respect to ground is going to be x sine theta square plus x common 1 minus cos theta whole square whole under root. So if you work on that, you'll get x squares, which is outside the root, so becomes x sine square theta plus, we have a sine square theta from here, cos square theta from there, that gives you a 1. Then we have a 1 from here, that gives you another 1, so you'll get a 2. And then you have a minus 2 cos theta over there, so minus 2 cos theta over there. So if you want, you can further work it out. I'll just quickly do it for you. 1 minus cos theta. I've done enough trigonometry. Trigonometry is what is going on. So what do you think is 1 minus cos theta? Can I write it in a compact way? Yes, we can use cos 2 theta formula as 1 minus 2 sine square theta. So what we get is 1 minus 2 cos theta is 2 sine square theta. So this is going to be 1 minus cos 2 theta. So this is going to be 2 is already there, then another 2 sine square theta by 2. So I'm just doing this because many a times you'll find that this kind of format gets reduced, and what you ultimately get is your xag, this part is going to be x times 2, and 2 is outside. I'll put a 2 first, 2x sine theta by 2. So that is your answer. That's your blue line in the clear over here. The movement will be 2 times x sine theta by 2. So that's your displacement, and the angle is, as you can see, the angle will be given by this diagram. So the angle, say if you want to know the angle with the horizontal, call it as phi, and that angle phi will be given by tan phi is equal to sine theta upon 1 minus cos theta. Again, in the reduced format, you'll have it in half angle. Sine theta, you can write it as 2 sine theta cos theta, and that one in sine square theta by 2, and one of the sine theta by 2 will get cancelled. So I'm not going into that. So the thing is, this is your final answer. And again, I'll emphasize what we use over here is the movement of A with respect to the wedge. And how did we find out that? We were keeping the wedge stationary, and instead of moving the wedge to the wall, we moved the wall to the wedge. We moved the wall to the wedge, and we can easily see that this would slide down. If the wall moves by x, this will slide down by x. So that was a key to find the answer over here. And a nice diagram with your angles, correct angles. This angle was your theta, so you did the vector. This was your x, and x is what is the key thing you figured out, angle theta. So finding this is not a big deal. You can apply cos rule over there to get that, and still you'll get the answer. What's the cos rule? The angle, the side over there, xag is equal to under root of x square plus x square minus 2x square, the sandwiched angle. The sandwiched angle is theta over there. So that's a square plus b square minus 2ab cos theta. So that's the same thing what we did over there. So this is by the Pythagoras theorem. This is by the cos rule, which is all the same. Okay, I'll give you one question that is going to be your last question, where you have wedge on wedge and pulley also, and maybe a movable pulley. So a movable pulley and a wedge on wedge. So that is like the ultimate question in these kind. Okay, so hopefully you get that, and that would be the end for this lecture today.